Welcome to the third day of Summer General Physics. In this fourth video, we'll be looking at motion that occurs in two dimensions. So two-dimensional motion can look quite complicated because you have an object that it's moving in maybe an X and a Y direction. Well, it turns out that analyzing this motion is actually simpler than it first appears, because often we can split the motion up into components and analyze the motion in each direction separately. So you can see in this example a car that's going around a corner. We can compare its final velocity and its initial velocity to find the change in its velocity in order to find its acceleration. Now, the velocity, acceleration, and displacement, we remember, are vectors. And it turns out it's possible to look at just one component at a time. So we can find the acceleration in just the x direction by looking at the final and initial velocities in just the x direction, and we can look at the acceleration in just the y direction by considering the final and initial velocities in just the y direction. In this way, we split up the problem into simpler chunks, and we can solve for each direction separately and then bring the components back together for a final answer. So here's a question for you. Let us consider the following controls on a car. You can have a gas pedal, brake, steering wheel. Which of these can cause the car to accelerate? So pause the video here, give that a bit of a thought, and come up with your answer. Okay, so now that you've had some time to think about that, which of these controls could cause the car to accelerate? The gas pedal, the brake, the steering wheel? Well, if we think about the gas pedal, that's probably the most obvious one. You depress the gas pedal and you expect the car to go faster, to accelerate, so that will cause an acceleration. The brake can cause an acceleration as well, because if you push on the brakes, then the car should slow. And a slowdown or a deceleration is a type of acceleration. Anything that changes the velocity it causes an acceleration. And then the steering wheel, well, velocity is both a speed and a direction, and acceleration is a vector. So if we change the direction of motion of the car, we will be changing the velocity vector, and that is also an acceleration. So all three controls can cause the car to accelerate, because an acceleration takes into account both the change in speed and the change in direction. So let's look at an example problem where we have a change in direction and we can calculate an acceleration. So in this example, Bob is on a Ferris wheel, and the Ferris wheel is turning clockwise at a constant rate. At some point, he's moving 3 meters per second directly downward, and then 4 seconds later, the Ferris wheel's rotated by 30 degrees, and we want to know what is the average acceleration that Bob experiences. So we should draw a picture of this problem and show the final and initial states of Bob's motion. So if this is our Ferris wheel, initially, and the Ferris wheel is turning in the clockwise direction, initially Bob is moving directly downward. So he would be here on the Ferris wheel, and his velocity would be straight down. So this is his initial velocity at 3 meters per second. And then at some point later, 4 seconds later, the Ferris wheel has rotated by 30 degrees. So if we draw a line out to where Bob is initially, 4 seconds later, that line will have moved by 30 degrees, and he will be moving in a direction like this that is also at 3 meters per second. And so we've drawn a picture of Bob's initial and his final velocity. Now we know that acceleration is defined as being the change in velocity with time, And since we have two-dimensional motion in both the x and the y directions, then we will want to split the acceleration up into x and y directions, and therefore his velocities up into x and y directions as well. So let's take a look at doing that. We want to take his initial velocity vector and his final velocity vector and split them both up into x and y directions. So first off, the initial velocity. That's the easy one. So if this is his initial velocity, or a coordinate system showing the initial velocity is downward, 3 meters per second. So if we make a bit of a table of his initial velocity, we can see that in the x direction, well, there is no component of his initial velocity in the x direction, it's all in the y direction. So we can say that his initial velocity in the x direction is 0, and his initial velocity in the y direction is negative 3 meters per second, meaning Bob is moving at 3 meters per second in the downward y direction. So then let's take a more careful look at his final velocity, and we need to split this final velocity up into x and y components as well. So if I imagine drawing a little coordinate system here at the tail of his final velocity, and I think about how this vector has been changing. Here the vector was straight down. As the wheel turns, the tip of the vector starts to swing away from the straight down direction. If I went all the way to the bottom, so if I considered his velocity here, it would be all in the negative x direction. So that velocity vector, as the wheel moved 90 degrees, the change in direction would be 90 degrees. So he would move, the velocity vector would move from pointing straight downward to 90 degrees in the clockwise direction, which would be in the negative x direction. At this intermediate point, the vector has swung only 30 degrees. So if Bob moves down 30 degrees, his velocity vector will swing away from the downward direction also by 30 degrees. So this would be a 30-degree angle. So if I redraw his final velocity vector with its own coordinate system, his velocity vector has a magnitude of 3 meters per second and makes an angle of 30 degrees with respect to the negative y-axis. So then I can think about splitting this vector into an x and a y component. So if I think about the sine of that 30-degree angle, then the sine of this 30-degree angle would be the opposite side, which is the x component, over the hypotenuse, which is 3 meters per second. So the x component would be equal to 3 meters per second times the sine of 30. And then that would be equal to, let's see, that will give me about 1.5 meters per second. And then if I think about the cosine of my 30-degree angle, the cosine is the y component divided by the hypotenuse. So my y component would be 3 meters per second times the cosine of 30 degrees, which would have a value of 2.6 meters per second. So now if I think about the final velocity, I have split his final velocity vector into x and y components. So the final velocity in the x direction is going to be equal to 1.5 meters per second, only I'd better specify that's a negative because his velocity vector is pointing in the negative x direction. And in the y direction, we have 2.6 meters per second. And once again, that's going to be in the negative y direction. So now I'm ready to find the x and y components of the acceleration. So the average acceleration in the x direction is defined as being the final velocity in the x direction minus the initial velocity in the x direction, divided by the amount of time it took to accomplish that change. So the final velocity in the x direction is negative 1.5 meters per second, and the initial velocity in the x direction was 0. And that change was accomplished in 4 seconds. So the x component of the average acceleration is going to be negative 0.375 meters per second squared. And I can do the same thing in the y direction. So the average acceleration in the y direction is the final y velocity minus the initial y velocity divided by the change in time. So we found that the final velocity in the y direction is negative 2.6 meters per second minus the initial velocity in the y direction, which was negative 3 meters per second, divided by 4 seconds. And that gives me a value of 0.1 meters per second squared. So now I have both an x and a y component of the average acceleration. So I should draw a picture of what the average acceleration vector looks like. So here are my coordinate axes, and the x component of the acceleration is negative. So it's negative, and it has a magnitude of 0.375 meters per second squared. And the y component is actually positive. So in the y direction, the component has a value of 0.1 meters per second squared. And then if I add the two components together, I get my average acceleration. So then I can find the magnitude of the average acceleration by using the Pythagorean theorem. So that's going to be 0.375 meters per second squared plus 0.1 meters per second squared. And then I take the square root of the whole thing, and that gives me a value of 0.39 meters per second squared. So that would be the magnitude of my average acceleration. I can also find the angle that the average acceleration makes with the negative x-axis. So I would find that by using the inverse tan inverse of the opposite side, 0.1, divided by the adjacent side, 0.375. And that would give me an angle of 14.9 degrees. So I would report that as being 14.9 degrees above the negative y-axis. Or if I needed to give my answer with respect to the the 14.9 degrees with respect to the negative x-axis. If I wanted to give my angle with respect to the positive x-axis, I could subtract 14.9 degrees from 180, and that would give me this angle. So that concludes this video. In the next video, we will be considering a special case of two-dimensional motion called parabolic motion.